talking about what SEAndroid is, what it used to be like probably 5 years ago, and kind of what it's like now if you were an attacker and if you wanted to actually break into someone's phone. So just a little bit about myself. My name is Jake Valleta. I am a manager at FireEye, Mandiant, and I joined Mandiant back in 2011, so I've been kicking around for quite a while, doing a number of different security-related job roles, from forensics to teaching external education to the feds, penetration testing, mobile security, all that fun stuff. My favorite thing in security, though, is Android security, and that started back in 2011 when I did join Mandiant, and I've kind of never looked back since then. I describe myself as an enthusiast, and I also like drinking beer, so if anyone wants to drink some beer after this, let me know. I'm based in San Francisco, so sorry I'm not an Alaskan local, but I am learning a lot about Alaska. It's very pretty here. I like how you guys have a very strong culture, it seems like. My Twitter handle's on there if you want to reach me. I'm really bad at Twitter, so it's probably not the best means to get a hold of me. I have a contact link at the end if you actually have questions, and I have a few business cards if anyone wants to shoot me an email after. So here's our agenda. We're going to start off talking about what SEAndroid is. Before we even started, people were asking what SE stood for. Hold on, we're going to get there in just a minute. We're going to talk about what it used to be like. Probably, again, this is only like 3 or 4 years ago on Android. And talk about what it's like now, how SEAndroid has changed the threat landscape for doing platform exploitation. So this doesn't really talk too much about app security. We're not talking about securing apps. We're talking about the platform itself, the Android operating system, and what the apps are running on. And we'll have some time for Q&A at the end. So those are always welcome. So some of my goals and hopes and dreams for the people in the room. Again, thanks for being here. My goal is to educate you on what SEAndroid is, not at a very professional level, but just to understand fundamentally what it does, how it works, why it's there. And also, if you are someone who is really interested in Android security or just pen testing or anything like that, is to give you a starting point. I think as we move forward, you're going to see a lot more talks about SEAndroid because it's fundamental to platform security. It's something that you're going to have to deal with if you're trying to find bugs on Android. And also, this bottom one here is my favorite. There's like 10 people so far today who are like, Android sucks, Android's garbage. And it's like, yeah, maybe it was terrible, but it's gotten a lot better. And there's a lot of good things going into Android. I'm not here to say it's perfect. It definitely has its flaws, and I'm aware of that. But there is a lot of good things that Google and other companies are doing to try to make it harder for attackers to compromise phones. If you look at some of the bug bounties for like the pwn to own, they're pretty expensive because it's not that easy anymore. So let's start by talking about SEAndroid and what it is. But actually, hold on. We need to talk about access controls before we can talk about SEAndroid. So at the most fundamental level, an access control is something that restricts a subject, like a person or a user, access to an object, something like a file or a socket or something like that. And the reason I bring this up is because there are 2 different models that we're used to in modern computers. The first is what's called a DAC, or Discretionary Access Control System. Who in here is familiar with Linux? Please, Linux. Excellent. OK, you guys are probably familiar with the Linux file permissions. We have read, write, execute, user group, other. That's a discretionary access control file system. This means that the subject can pass controls onto other objects. In Linux, if I create a file, that's my file. I can do what I want with that file. I can share it with other people. I can change those bits because it's my file. And I like to point out that this could be either accidental or intentional. Right? You could want to share things, but you could also accidentally do something wrong here. Contrast this to what mandatory access control is. This is where security is enforced by a policy administrator. Right? You might own the file. That's great. But there's somebody else enforcing the permissions for you, and you don't really have the same level of control that you did before. You cannot pass control to another subject. And you're also not allowed to override the policy. The policy is sent somewhere else, and you are operating in your space, but there's not much you can do. Some examples here are, 1, SEAndroid, which we're going to be talking about. And the other one I like to bring up here is Trusted BSD, which is what Apple uses on the iOS framework for sandboxing applications. So just a little note on sandboxing. Both Android and iOS are sandboxed operating systems, which means that applications run separate from each other. And it's not possible, in theory, to gain access to another application's data. On Apple, they use Trusted BSD framework in the kernel. And on on Android, historically, they use the Linux DAC system. But we're going to talk about how that's changed. So just some weaknesses. You guys said you're familiar with Linux. Just some weaknesses that I think, and I think others would agree, with the traditional Linux DAC architecture is, first off, we have this root user. And root is way too powerful. Root doesn't make a whole lot of sense on your phone, right? On Linux or on a server, it may make sense to say sudo rmdir, but that doesn't really make a lot of sense on your phone. There's really no one process or no one user that should have access to all the data on that phone. And because Android is based on the Linux kernel, we have a root user there, which means that people tried to become root to compromise your phone. Second is that whole principle of discretionary access control is that the objects are entirely at the discretion of the owner, which means developers make mistakes and they do bad things, and we see problems. I've seen this so much over the past 5 years. And also certain objects, things like sockets. You guys are familiar with sockets for like network sockets or Unix sockets. Things like ioctl calls, the ability to talk to the kernel. We don't have the ability to check security on these objects, which is a problem. And again, I already talked about root user, but there's also sudo accounts, right? Sudo does not make sense on Android. Luckily, it's not there. But the su binary is present, which can be used to change to another user, which is something that you really should not see in a production device. And we really can't get too fine-grained in terms of security controls with the traditional Linux DAC. We'd have to have hundreds of users, hundreds of groups. It would be really complicated and really hard for us to actually have fine-grained controls on a specific socket or a specific file, which is something that hopefully SEAndroid will make easier for us. So let's just walk through a quick example here. You guys, most of you said you're familiar with Linux, so I'm not going to spend a whole lot of time on this. But in general, we have 9 primary bits for handling access control on Linux. We have our users, our group, our other. Those are our subjects. And for each of those, we have these permissions, read, write, execute. Now, there are some extended ones that have been added, and that's great. But this is where we're going to kind of stop the conversation here. And you can manipulate these however you like to restrict access to whom you'd like to restrict access. So let's do an example here. So let's say we have Alice. Alice is our Linux user. And she wants to create a file, and she'd like to store sensitive information in that file. So she creates a file. Now, Alice owns this file, so that's hers. Well, now Alice wants to share something with Bob. Sharing is caring, and Alice owns the file again. She can change the file to do whatever she'd like. So Alice is not really sure what she's doing, so she decides to set that other bit, which is not user, not group, everything else, so that other users can read the file. And now Bob can read the file. But what she doesn't realize is that now all users are reading that file, and that's a problem, because along comes Eve. And Eve is not a nice person, and Eve accesses that file with sensitive data, and Alice is sad. Now this sounds silly, but this is real life. I've tested in so many Android apps that, for example, a voicemail application that was sharing the voicemail files using file permissions. And that doesn't make sense. There are better ways to share files, especially your voicemails. No one else should be even accessing that. But by setting the other bits, now I'm not saying this is intentional, it was probably accidental, but that's not right. And it shouldn't be up to an app developer to actually make a mistake that grave. Okay, so now we can actually start talking about SEAndroid and SELinux here. So this has been around for a long time. It was originally developed by the NSA, go the NSA, back in 1989. But then around 2012, it was decided that it was going to be ported to Android. Now, for those asking, security enhancements is where the SE comes from. I just call it SELinux. For Android, it's SE for Android. I just call it SEAndroid. And just a quick little timeline here. I also want to define this acronym here for everyone, because I'm going to be mentioning the AOSP a couple of times. When people say Android as a core, it's the AOSP. This is the code base that's huge, that Google maintains, that is Android. All the OEMs, all the third parties, they take this code base and they do something with this code. So Google decided to add it back in 4.2. I believe that's Jelly Bean. That was back in the end of 2012. It wasn't doing anything. It was just there. I'm sure they were testing it internally. A little bit year later, in 2013, we saw SEAndroid click into permissive mode, which we're going to talk about in the next slide. And then more than a full year later, by 5.0, which is Lollipop, we finally saw it click into enforce mode, where it was actually basically doing something. And since then, it's been in enforce mode and required for all versions of Android going forward. Google's tried very hard and made it very complicated to actually turn off SE Linux, or SEAndroid. You may hear me call it SE Linux. I mean the same thing, really. So in permissive mode, for those of you coming from like a networking background, this is like your IDS, right? We're logging violations on the device, not to some server. But we're not really doing anything. We're not stopping things. We're not restricting behavior. We're just kind of logging things. Now, this was, again, mostly to make sure that app developers and platform developers knew what they were doing before they turned it on, because it was kind of a big change. But enforcing mode is like the real deal. This is your IPS. This is actually blocking and logging your violations. Whenever an app or anything tries to do something it's not allowed to, it's going to block it at the kernel level, and it's going to log that if it wants to. And this is, again, required. You have to do this now. You may see a phone that comes out of some shop in China that's not very well written that might not be using it, but if you're using real Android, you have to use this going forward. So what are the goals here? These goals are basically the weaknesses of the Linux stack, right? The first one is there's a lot of high-value targets on Android. And I'm not talking about apps. I'm talking about daemons running in the background. So for example, this is kind of a moot point now because we don't have this anymore, but remember external SD cards? You could plug them into your phone. That was cool. For some reason, we don't do that anymore, but think about that. Some service needs to mount that SD card, check it for errors, do all that stuff. That's something that a root user would need to do. So as you'd expect, that service is running as root. Or how about the service that installs other apps? It needs to have control of the file system. It needs to create directories. Again, these things are running as root, which makes them a very high-value target if you're trying to compromise a phone. Other things, remember I told you we couldn't label sockets. That was like a huge weakness. A lot of internal daemons on Android use Unix sockets to do IPC, or inter-process communication. And the problem is there was no way to enforce security on the socket layer. You had to do it on top of that, which is always going to be a problem because people don't know what they're doing. Also, I mentioned that apps are sandboxed, meaning they can't access their own data, other apps' data, using the Linux DAC. But we can actually add SEAndroid on top of that to stop that stupid example where Alice shares the file with Eve. Because with SEAndroid enforced, you can't change that bit. And if you do and someone tries to access it, the policy would actually restrict it. And finally, and most importantly, that root user needs to be neutered, right? We need to have some way to make it not attractive to want to compromise the root user. So a lot of times you find exploits now, they either go straight to the kernel or they'll have to bounce around to finally get to their goal. Because even if you're running as root, who cares? The policy applied to that particular process is not going to get you to the point where you want to accomplish your objectives, which is probably to compromise someone's phone. So again, we're not going to talk too much about how labeling works and how all this stuff goes down in the back end. I just want you to point out some definitions here so we're all on the same page. So in SEAndroid, everything gets a label. And everything, I mean objects. So files, sockets, properties, services. Anything that's considered an object gets a label. That is called the domain for a process. Or for a file, it's called a type. Now, type and class get a little confusing because the class is the category of an object. So for example, we have this thing here. It's called my file. That's our label. But it's of class file because it's a file. But we could also have properties. We could have sockets. That's the type of the category.